In my previous Fourier video, I explained Fourier analysis in general terms, and I covered the DFT equations in some detail in relation to a complex discrete signal that is n samples long. If any of these terms sound strange to you, I suggest you watch that video first before continuing with this one. I explained how these equations represent general sinusoids as discretely sampled functions that are also n samples in total length, and that can contain a variable number of wave cycles in that total length. In so doing, I mentioned that the frequency f dictates the number of whole cycles in any such sinusoid. In this video, I'll go into more detail about this frequency variable f. To get the full set of Fourier coefficients for a signal, you need to apply these forward DFT analysis summation formulae for every single frequency that could possibly exist in the signal. But how can we know what range of f values to use to ensure we're not missing any frequencies that might be present in the signal? And what are negative frequencies anyway? This is what I'll be talking about today. There are two aspects to the discreteness of the discrete Fourier transform, or DFT. The first is discreteness in the spatial domain, and the second is discreteness in the frequency domain. I explained the spatial domain discreteness in the previous video, that the input signal and all the sinusoids are only known or calculated at discrete points in space over a total of n integer positions, those positions which I describe using the variable k being labeled from 0 to n-1. However, I only briefly showed you an example of discrete frequencies when I explained the meaning of frequency in the Fourier sine and cosine terms. So let me emphasize that again here. The frequency f in all such terms dictates the number of complete cycles in any sinusoidal waveform. Remember, all sinusoidal waveforms used in the DFT are represented as discrete signals that are a total of n samples long, but within that n sample long waveform there are contained a variable number of whole wave cycle undulations. The key concept here is that only a whole number of complete cycles can be represented in any Fourier sinusoid for the DFT. You can't have half cycles or other partial cycles. It must be only a whole integer number of full cycles. This is what it means to have discrete frequencies. For the reconstructed harmonic waveforms in the inverse DFT, the phase of those whole cycles can be anything we want. In other words, we can start our whole cycles at any point in the sine or cos wave cycle. That's fine, but we can only use waveforms with a whole number of complete cycles, and that whole integer number is the value of f, the frequency, in our equations. So f cannot be any fractional number. It must be either 0 or an integer. In general, frequency means the number of cycles of signal amplitude oscillation per some unit, such as a unit of time or space. For time-varying electrical or audio signal fluctuations, we commonly use 1 second as the unit of time, so a frequency value of f means f cycles per second, or f hertz. However, there's no absolute reason why we have to use 1 second as the base unit to measure frequency in time. For example, we could talk about cycles per year for some slowly oscillating quantity. Some plants have an annual flowering frequency of 3, meaning they produce flowers 3 times per year. We can similarly define a unit of space for describing the frequency of some repeating pattern being observed per unit of length, like per mile. All those examples used units of some absolute physical quantity in time or space. However, the DFT takes in a discrete signal, which is just a list of n values. It has no intrinsic means of representing absolute physical measures like seconds or kilometers. In this scenario, the one constant baseline measure we do have for any given discrete input signal is the total length of the signal, which is the total number of samples in the signal, which I'm calling capital N. So, for a discrete signal that is a total of, say, 6 samples long, we could use that total length of 6 samples as our base unit, and measure all frequencies relative to that base unit. So, a harmonic of that signal, with a frequency value of f equals 1, means a sinusoid that makes one complete cycle of oscillation of its amplitude in 6 samples, returning back to where it started by the beginning of the 7th sample, if we were to extend the number of samples. Perhaps a better way to visualize this is as if the 6 samples form a cylinder. So what we previously called the 7th sample is actually the 1st sample, like this. So that's why, when starting our sample count from k equals 0, we only go up to k equals n minus 1, and not k equals n, because k equals n is a repeat of k equals 0. In other words, the sample value at k equals n is the repeat of the first value in this harmonic or wave. This is the same for all sinusoids in the DFT, regardless of frequency. This is what we mean when we say the harmonics and waves of the Fourier transforms are cyclic. This cyclicity is a fundamental feature of Fourier descriptions of otherwise non-cyclic patterns. You'll encounter some of the consequences of this cyclicity as you learn more about the properties of the Fourier transform. So that example showed a frequency of 1, meaning the waveform made one complete cycle over 6 samples. A frequency of f equals 2 means the waveform makes 2 complete cycles over the 6 samples. A frequency of f equals 3 means it makes 3 complete cycles in 6 samples. So, in general, for discrete Fourier analysis of a discretely sampled signal consisting of n samples, frequency is measured in the unit of n. That is the total number of samples in the signal. A frequency value of f means f cycles per n samples, expressed mathematically as f 2 pi over n or 2 pi f over n. Finally, because the f value is relative to the sample size, this implies that a specific f value represents in absolute terms a different frequency when applied to signals of different sizes, assuming the interval between samples is the same in all these signals. For example, f equals 2 is a higher frequency for a signal of size 4 samples compared to f equals 2 for a signal of size 6 samples, as shown. This dependency of frequency on sample size has some important practical implications, but I'll discuss those some other time. Looking at the inverse Fourier formulae, you can see that they use harmonics over a range of frequencies from negative to positive, with 0 in the middle. I'll explain what a frequency of 0 means in the next section, but what's a negative frequency? I think the thing that confuses some people on this topic is that when they hear the word frequency, they don't think of the actual frequency in itself, but rather they think of the thing that is fluctuating at that frequency. You see, a sinusoidal waveform is made up of some quantity that fluctuates over a range of space or time. The quantity that fluctuates may represent some physical thing like the height of the surface of water relative to some reference level, or the strength of an electrical charge. Of course, it may also be some abstract general quantity that doesn't need to represent any specific physical thing. The point is that the wave itself is the fluctuating quantity. In addition to, and quite distinct from, the wave itself, are the parameters we use to describe certain characteristics of the wave. These are its amplitude, its phase, and its frequency. See my video on Photology 2 to learn more about this in detail. So, the frequency is just a number that describes how many times some value fluctuates over some range. That number is the frequency. The wave is the actual fluctuating value itself. What I'm trying to get you to separate here is the number inside these brackets, that number is the frequency, and the result of this function. That result is the fluctuating amplitude value that fluctuates at that frequency over some range to form the wave. Once you get that distinction clear in your minds, you can easily see that a number that represents a frequency can be negative or positive to enable various mathematical operations involving frequency, without altering the fundamental nature of the wave itself or the physical thing that the wave might be representing. If I show you a sign with a negative frequency, you might get confused trying to figure out what it represents in the physical world. But if I show you this sum, all of a sudden a frequency of -5 seems trivial because you can see it's part of some arithmetic. Okay, But you might be thinking, well, the result of that specific frequency arithmetic example ended up with a positive number in the sine function. What if the sum were the other way round, and we ended up with a sine with an overall negative frequency in it? What do the actual waves, the sine and cosine waves, of those negative frequencies look like? Well, it's very easy to find out. We can just open up a spreadsheet and plot them. So, here is the plot of the output of a sine function and a cosine function, with the term in their brackets, which I'm calling x, showing increasing positive values. So, this is the situation where the frequency f is positive. This plot is for only one specific frequency that is not changing. The value along the horizontal axis is increasing because k is increasing in this term here, but we're lumping the result of this term into one variable, x. And here we have the same sine and cosine, where the frequency f is the same absolute value as before, but this time it is negative, so x is also negative. And again, the increasing values of x, whether that is increasing in the positive direction or negative direction, represent the increasing values of the k term in the full formula. Notice the symmetries here. The plot for the negative frequency sine wave is the inverse of the equivalent positive frequency sine. But the plots for the cosine function are identical, whether the frequency is negative or positive. You can see these symmetries emphasized if I simply reflect the plots about this zero-angle line, like so. In doing this, I'm aligning the waves so the value of the wave amplitude at the same value of k is shown at the same position along the horizontal axis for each wave, regardless of whether f is positive or negative. This means that if you take the value of the sine wave at some k position in the positive frequency plot, and the value of the negative frequency sine wave at the same k position will be the negative of the value of the positive frequency sine wave. But for the cosine wave, the two values of the waves will be equal to each other at any k position along the horizontal axis, regardless of whether the frequency is positive or negative. Here I express those relationships with mathematical notation. So sine of a negative frequency equals minus the sine of the equivalent positive frequency, and the cosine of a negative frequency is exactly the same as the cosine of the equivalent positive frequency. The type of symmetry seen with the cosine wave is called even symmetry, and the type seen with the sine wave is called odd symmetry. Mathematicians describe any functions that show these types of symmetries as even functions and odd functions. So these symmetries are not unique to pure sine and cosine waves. You see, in order for the Fourier transform to be able to represent all possible harmonics in any general signal, it needs to use these two pairs of pure sine and cosine waves. I'll explain more about why it needs to use these two pairs of waves in my next video. So for now, just take it as given that it needs one pair of waves with a standard cosine and sine function using positive frequencies like this. We'll call this the standard sine pair. And it also needs a pair of waves with these shapes, which correspond to the sine and cosine that use negative frequencies. We'll call this the negative sine pair. Now, it doesn't matter how we generate these two pairs, as long as we can represent them somehow in our Fourier equations. So far, I've shown you how we represent them with the standard cos and sine functions, using positive frequencies to generate the standard sine pair and negative frequencies to generate the negative sine pair. But is there a way we could represent these two pairs of waves using only positive frequencies in both cases? Well, yes, it is possible. We don't need to do anything special for the standard sine pair because these already use positive frequencies. So the real question is, how can we represent the negative sine pair of waves without using negative frequencies? We've already seen that the cosine wave for a negative frequency is identical to the cosine for the positive version of that frequency. So we could just replace the negative frequency cosine with the positive frequency cosine. We've also seen that the negative frequency sine wave is just the positive frequency sine wave multiplied by -1. So we could define a new function. Let's call it the nis of x, which is defined as the negative of the sine of a positive frequency. This means that the nis of a positive frequency is identical to the sine of a negative frequency. so we can replace the sign of a negative frequency with the nis of the corresponding positive frequency. So now we can do the Fourier transforms using only positive frequencies, but we need to do it in stages because we'll have to use the same positive frequency range twice, once using the standard sine pair and once using the negative sine pair, defined using our new wave function, the nis. In both parts, positive frequencies will range from f equals +1 to f equals plus f max. We'll also use a separate equation for the special case of zero frequency, which I'll describe in more detail later in the video. Because we're using the same frequency range twice, we'll get two sets of Fourier coefficients for the same frequency, f, one from each equation. So we'll need to distinguish them from each other somehow. In this example, I label the Fourier coefficients calculated with our new nis function with a lowercase n, as shown. However, due to the even and odd nature of the sine and cosine functions, we don't need to complicate things using three separate equations and two different types of sine function. We could, alternatively, get exactly the same values for our Fourier coefficients if we just used one summation using the ordinary standard sine and cos function pair over one continuous range of frequencies, a range that includes negative frequencies on one side and positive frequencies on the other, with zero in the middle. This is mathematically much simpler because this is all one continuous range and we don't need to separate out three subsets of Fourier coefficients. Also, we can represent this version of the Fourier equation using the complex exponential form, which allows a lot of useful mathematical analysis to be done with it, whereas we can't do that using the three separate equation DFT that avoids negative frequencies because Euler's simple formula doesn't apply if we use this nis function instead of pure sine and cosine. Because, as you'll recall from my first Fourier video, this exponential form depends on using Euler's formula. So, negative frequencies don't represent some fundamentally different magical waves that travel backwards in time or anything like that. They just allow us to represent the shapes of the two pairs of waves that we need for Fourier analysis, using one continuous range of frequencies with just the standard sine and cosine functions. However, there's more to it than simple mathematical efficiency. It turns out that using a continuous negative to positive number line for frequencies also gives us a more direct mathematical description of real-world physical phenomena. You might recall this simple demonstration of Fourier optics from my first video where I used the PUMA plane wavefront generator, or PUG, and a simple convex lens to form an optical Fourier transform of an aperture mask image. Well, here you can see that the distribution of light in the Fourier plane, which can be described by the mathematics of a Fourier transform, shows a symmetrical pattern. Mathematically, we could describe all the frequencies in X with positive frequency cos and nis functions on one side, and positive frequency cos and sine functions on the other side, and a separate number for the light right in the middle, and we can do the same for the y frequencies going up and down. Or, alternatively, we can mathematically describe the same light distribution with a continuous sweep of frequencies in the x direction, using only the standard cos and sine functions, if we use negative values for frequency in those functions on one side, going via zero frequency in the middle to positive frequencies on the other side, and likewise for the y frequencies. Either way, the light is the light. It doesn't care if we use a clumsy and unnecessarily long-winded way to describe it because we're afraid of using negative numbers for some reason, or if we use a simple and elegant way to describe it. I'll say more about two-dimensional Fourier transforms and Fourier optics in other videos, but I just wanted to show that negative frequencies are not strictly necessary for Fourier analysis, but are just a more efficient mathematical way to generate the specific wave shapes that we need to use for Fourier analysis. The negativeness of those frequencies doesn't say anything unique or fundamental about the nature of any physical system that we might use Fourier analysis to model. The lowest frequency representable in any signal, discrete or continuous, is a frequency of 0. A wave at that frequency is simply a constant amplitude value that doesn't change all throughout the signal. In the language of Fourier harmonics, some people refer to this as the zero-order harmonic, or the DC offset, because harmonics at all other frequencies fluctuate equally above and below 0, which means they all have a mean value over the entire signal of 0. But the 0 order is the only harmonic that can impart some absolute non-zero mean value to the reconstructed signal. The phase of a wave with 0 frequency simply translates to the level of this constant amplitude value, because phase determines whereabouts on the up-down amplitude cycle a sinusoid starts. So the phase of the 0 order harmonic determines where it starts, and the fact that the frequency is 0 means that where it starts, there it stays throughout the whole length of the signal duration. Now to the other end of the frequency scale. If you think about it, the fastest frequency that can possibly be represented in any discrete function is the one where the higher amplitude point of the cycle is on one sample and the lower amplitude point is on the very next sample, and this variation repeats from the third sample onwards. So this frequency equates to one cycle per 2 samples. Of course, this is the same frequency-wise if we had started on a lower point of the cycle and then went to the higher point of the cycle in the next sample, etc. This means that for a signal of total n samples, this maximum representable frequency has a value of n over 2 cycles per n samples, often just written as f equals n over 2. This special fastest frequency representable is called the Nyquist frequency, named after Harry Nyquist, who made important contributions to communication theory in the early 1900s. For this reason, to ensure that you cover all possible harmonics for any general signal, the DFT equations must use a frequency range from f equals 0 to f equals Nyquist, or n over 2. But recall that the DFT can only use whole integer frequency values, so this special highest Nyquist frequency, that of f equals n over 2, can only be exactly represented by a single harmonic in cases where n, the total number of samples in the signal, is even, such that n over 2 is an exact integer. For signals where n is an odd number, the highest integer frequency representable in the DFT as a single harmonic will be just below the Nyquist. You can understand this intuitively from the examples shown in the graphic. So, for the DFT of a 5-sample signal, because we can't use the exact Nyquist frequency of f equals 2.5, we need to use the rounded down value of f equals 2 as our maximum frequency, and this is half a cycle lower than the full Nyquist frequency. But that's a limitation of the DFT formulae. It's not a limit of the signal itself. In practice, we can get a 5-sample signal with single-sample alternating up-down values corresponding to the exact Nyquist frequency of f equals 2.5. So, if we submit this signal to DFT analysis, how can the DFT represent this effective f equals 2.5 frequency fluctuation when the DFT itself can only use sinusoids with frequencies up to a maximum of f equals 2 in this case? Well, one of the clever things about the DFT is that it can reconstruct the equivalent of an exact Nyquist frequency in such cases by using a mixture of waves with some at the sub-Nyquist frequency combined with one or more lower frequency waves. For example, in the case of this signal where n equals 5, it uses the f equals 2 and f equals minus 2 sub-Nyquist harmonics plus the f equals plus and minus 1 lower frequency harmonics to recreate a perfect equivalent of an f equals 2.5 exact Nyquist fluctuation. I can demonstrate this with my Fourier spreadsheet that I introduced to you in my previous Fourier video. So here is a DFT calculation for a 5-sample signal. Currently the signal is in the form of a ramp function, but let's change it to be an exact Nyquist fluctuation, equivalent to a frequency of f equals 2.5, which, as we know, the DFT can't represent as a single harmonic in this case. Now, if we go over to the sheet that displays the harmonics, you can see that the f equals plus and minus 2 sub-Nyquist highest frequencies try to imitate the signal, going above and below the 0 line at alternating sample points. But because they're just below the true Nyquist frequency, they have an inevitable build-up of phase shift, as they progress across the sampling frame, from the center outwards in each direction. So the fluctuations about zero are not even across the signal, as we need them to be. They have smaller amplitude fluctuations near the extremities and larger fluctuations near the center. But look here, the lower plus and minus 1 frequency harmonics exactly compensate for that unevenness by being negative near the center, where the high frequency harmonics fluctuate with greater amplitude, and positive towards the periphery, where the higher frequency harmonics fluctuate the least. So when you add up all these harmonics, this balances out the uneven single sample fluctuations. And if we go to the final Fourier synthesis sheet, we see the end result of adding all these frequencies is a perfectly even alternating sample signal that exactly matches our initial f equals 2.5 exact Nyquist signal, even though we didn't have an f equals 2.5 harmonic to do it with. So, when calculating a DFT, the practical limits of integer frequencies will be the range f equals minus to plus Nyquist for signals with an even number of samples, or f equals minus to plus sub-Nyquist for signals with an odd number of samples. But even this is not quite the full picture. There's one more practical detail you need to know. Because we're using discretely sampled sinusoids, and due to the symmetries and cyclic repetitiveness of the sine and cosine waves, the sampled values of the sine and cosine waves at the exact positive Nyquist frequency turn out to be exactly the same as the sampled values of the sine and cosine waves at the exact negative Nyquist frequency. This means that when n is even, such that we do have an exact Nyquist frequency available to us for the DFT, we must not use both the positive and negative exact Nyquist frequencies in our DFT range, or we'll overestimate the amount of Nyquist fluctuation in our signal by a factor of 2. This is because we'll effectively be analyzing for the exact same frequency twice. Again, I can illustrate this using my Fourier spreadsheets. This one is for a signal with n equals 4, which, being an even number of samples, means that we can have an exact Nyquist frequency of 2. However, instead of looking at the signals and harmonics, we'll just concentrate on the sampled values of the sines and cosines used in the DFT calculations. You see, the values used at the lower frequencies, where f equals +1 and -1, are different to each other in respect of the values of the sine wave component, due to the negative frequency sine wave being flipped compared to the positive frequency sine wave. So using the frequency -1 will give potentially different correlation values with the input signal compared to using the f equals +1 frequency, so we get additional information correlating with both f equals 1 and f equals -1 frequencies. Now look at the sample points in the sine wave between the plus and minus exact Nyquist frequencies of f equals 2. Although the sine wave is flipped between the two, the actual sample points on the sine wave that we use in the discrete Fourier calculations are exactly the same between the two. So to use both the positive and negative Nyquist would give repeat information. It would be as if we'd used the zero-order frequency twice, or any other frequency twice. So it would overrepresent the Nyquist frequency in the Fourier coefficients if we did this. Now look at the spreadsheet for a signal with n equals 5. Our highest integer frequency here is f equals 2, but although this is the same number, 2, as in the previous case, remember that this actually represents a slightly lower frequency than before because it represents a proportion of the total sample points. So in this case, f equals 2 is a sub-Nyquist frequency. The actual exact Nyquist frequency is f equals 2.5, which is unavailable in the DFT formulae. So note that this time the sampled values of the sine wave for plus and minus f equals 2 frequency are not identical to each other. So we do use both f equals +2 and f equals -2 sub-Nyquist frequencies in our DFT for a sample size of 5 because we're not duplicating information. Now, I know the exact Nyquist of f equals 2.5 is not allowed in the DFT, but just look what happens when I do use a frequency of plus and minus 2.5 in this case. You see, the positive and negative exact Nyquist give identical sample values on the sine wave, just as with our smaller sample. So this exact Nyquist identity is not unique to cases where the exact Nyquist frequency is an integer. It's a general truth, but it only becomes a practical issue to exclude one of the Nyquist frequencies in the DFT when it exists as an integer frequency, because those are the only types of frequency allowed in the DFT. It is in fact a general truth that the sampled sine wave values for all integer frequencies in any size DFT will be different in terms of their positive and negative frequency versions, with the sole exceptions of the exact Nyquist and the zero-order frequency. So, we must only use the zero-order frequency once, and we must only use the exact Nyquist frequency once, in either its positive or negative form, but not both. By convention, we often choose to use the positive Nyquist in such cases. So, from all this you can see that the detailed integer range of frequencies used in the DFT are from minus sub-Nyquist to plus sub-Nyquist for a signal with an odd number of samples, and from minus just before Nyquist to the positive exact Nyquist in cases where the number of samples is even. Finally, think about what these ranges imply in terms of the total number of discrete frequencies present in the DFT of a signal of any size n. First, consider a signal with an odd number of samples, such as n equals 5. The frequency range is -2, -1, 0, +1, and +2, which makes a total of 5 frequencies, the same number as the number of samples in the signal. Now consider a signal with an even number of samples, like n equals 6. Here we have a frequency range starting at minus just before the Nyquist, that is -2, then -1, 0, +1, +2, and the exact Nyquist, +3. So this comes to a total of 6 frequencies. Again, this is the same number of frequencies as we had samples in the input signal. So you can see that for a signal of any size n, whether n is odd or even, the total number of frequencies in its DFT is exactly the same as the number of samples in the input signal. This is why, whenever you see an image and its DFT, they're both of exactly the same dimensions as each other. In the spatial domain, the pixels represent different sample points in space, and in the Fourier domain, the pixels represent different frequencies. In the previous video, I gave an intuitive introduction to Fourier analysis, introduced the DFT equations, and described the type of input signals used in the DFT. In this video, I've gone into practical detail about the concept of discrete frequencies, negative, zero, and Nyquist frequencies, and the frequency range used in the DFT. I also introduced the concept of even and odd functions and symmetries. In my next video, I'll go into more detail about the outputs of the DFT and explain how harmonics are described using the values of the Fourier coefficients. In so doing, I'll introduce the concept of using the standard sine and cosine as a pair of basis functions. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.